Hello everyone, we are from Group 12, a team of engineering students from University Technology Petronas. Today, we'll be presenting our project on solar PV based cooling system for an academic buildings at UTP. Now let's go through the outline of our presentation today. There's 6 major contents for our presentation today that state in this slide. First, which is our first content, the identifications of need. Our main goal is to design and implement a cooling system using the solar PV technology. This will help to reduce energy costs and lower the carbon footprint for our campus. We have chosen UTP in Bandar Seri Iskandar, Perak for our project. The university location has a great condition for harnessing solar energy efficiently. So, by using renewable energy source, we aim to be more environmentally responsible and sustainable. The abundant sunlight in these regions provide a reliable solution for our campus cooling need. So, the cooling system must work consistently from 8 a.m. to 6 p.m., the building's operations hour. We are designing a hybrid system to ensure optimal performance during peak hour. Our expected outcome is our proposed systems aim to create a comfortable indoor environment conducive to learning and productivity. By utilizing solar PV technology, we expect to enhance the overall energy efficiency and sustainability of the campus.
Now for the literature review. Approximately 40% of global CO2 emissions are caused by the combustion of fossil fuels to generate electricity for use in industrial, commercial, and residential sectors. Malaysia's energy generation is primarily reliant on fossil fuels, with 43% coming from coal, 41% from natural gas, and only 16% from renewable resources. The industrial sector consumes the most energy at 50%, followed by commercial activity at 30%, and residential consumption at 20%. In Malaysia, fossil fuels account for 88.4% of energy generation, with 37% coming from petroleum, 36% natural gas, and 6% renewables. Industrial operations consume the most energy by sector, accounting for 49%, followed by cement industry 48%, and commercial 30%, residential at 20%. This excessive reliance on fossil fuels adds significantly to CO2 emissions, emphasizing the critical need for a shift to renewable energy sources in order to alleviate environmental damage and meet energy demands responsibly. Malaysia's energy generation mix consists of 45% natural gas, 38% coal, and 17 renewable energy sources. Decarbonizing the power generation sector by enhancing the share of renewable energy is critical for addressing climate change and ensuring a reliable and sustainable energy supply for the country's future. Malaysia is located near the equatorial zone, making solar energy one of the most significant renewable energy resources available. Malaysia receives an average solar radiation of about 400 to 600 mJ meter squared per month. By 2023, the installed capacity of solar energy had surged to 2,600 MW, up from 1,493 in 2020, demonstrating substantial growth in the solar market driven by supportive government policies and initiatives. And now for the detailed design drawings. Figure above is a network diagram of proposed solar PV system. Solar panels convert sunlight into direct current electricity. A solar inverter converts the direct current electricity into alternating current. The AC electricity generated by system is regulated by a control panel before being used to power the cooling system. The system has the option of battery storage, which allow excess electricity generated during periods of high solar output to be saved for later use. Solar energy is a renewable source, but it is intermittent, which means it cannot be harnessed at night or on overcast days. For the system to be more reliable, it is connected to the local power grid and connected to a battery storage where excess electricity generated can be stored. These are the 2D views of the drawing of our solar PV. Unfortunately, due to some error, we cannot obtain the dimensions. And this would be the 3D view of the drawing. This diagram is the floor plan of our chosen block, which is block 17. These dimensions are measured in imperial units, feet. The square foot of the entire block is 252 feet times 88 feet. Assuming all the floors are equivalent, we have done our calculations.
Moving on to the detailed design calculations. For this project, several assumptions are required. The location that we have chosen is at block 17, which is the mechanical engineering block. By making use of Google Map, we are able to measure roof area, which is 739.56 meters squared. The number of classes is 10 classes per floor, and there are a total of 3 floors. The cooling load per classroom is 5 kilowatt with the operation time of the AC of 10 hours daily and 5 days weekly. The solar irradiance is daily average of 5 psh and the efficiency of the solar panel is 20%. Moving on, the total number of classroom is calculated to be 30 classroom with a total cooling load of 150 kilowatts. Solar PV system, the total operation hour of the cooling system is 50 hours per week with a daily energy requirement of 1500 kilowatt hour. Thus, the required solar PV system output is 1500 kilowatt. Moving on to the calculations. So for the module area, the purpose is to determine the total number of solar modules that can fit on the available rooftop space and calculate the total array capacity. By knowing the rooftop size and module efficiency, we can estimate the total power output of the solar array. For the AC system size with the rating, it is to adjust the total power output for real-world conditions. The rating accounts for losses due to factors like temperature, shading, and system inefficiency, giving a more accurate estimate of usable AC power. Inverter sizing with DC-AC ratio. It is to ensure the inverter can handle the power output from the solar array. The DC-AC ratio helps in selecting an inverter that matches the power need of the system, ensuring optimal performance and reliability. The string size is to determine the number of modules that can be connected in series for optimal voltage. Calculating the string size ensures the system operates within the voltage limits of the inverter, maximizing efficiency and safety. Next, by making use of photovoltaic geographical information system by the European Commission, we are able to find out the PV output and radiation data over the year. The calculations that we have made earlier are specified inside the simulation software called PVSYST. The results of this simulation will be explained in the next section of the presentation.
Simulations aid project planning by offering clear visuals and predictions. They model future energy use, identify potential issues, and test strategies for efficiency. We had used a software called PVSYST to create estimation or prediction graphs to further support our project planning. This graph displays the monthly AC energy consumption for the first year, measuring in kilowatt hours. It shows that the highest energy usage occurs in January with a noticeable drop in the following months, stabilizing from April onwards with relatively consistent consumption. The chart highlights the variations in energy usage throughout the year. For this graph, it shows both the monthly AC energy consumption and the total electricity load for the first year in kilowatt hours. The blue bars represent the AC energy usage, while the gray bars indicate the total electricity load. The chart reveals that AC energy consumption is a significant portion of the total electricity load each month, with the highest total electricity load occurring in January and December. The data actually highlights the seasonal variations in energy usage and overall electricity demand. For this graph, it predicts the electricity net generation over a span of 25 years in kilowatt hours. The chart shows a gradual decrease in net electricity generation from approximately 200,000 kilowatt hour in the first year to around 170,000 kilowatt hour by the 25th year. This decline may indicate factors such as aging equipment, reduced efficiency, or other long-term operational changes affecting electricity generation capacity. In conclusion, these graphs offer important insights into energy use and production for our project. The monthly AC energy consumption graph shows peak usage times, helping plan for energy supply and efficiency. Comparing AC consumption with total electricity load highlights AC's impact on overall demand, guiding optimization. The long-term net generation graph shows a 25-year decline, indicating that need of maintenance or upgrades. These simulations aid in resource allocation, maintenance planning, sustainability, and budgeting, ensuring an efficient and effective energy system. In the end, we had chosen Hyundai Energy Solutions panels for our project. Choosing monocrystalline solar panels with 400 watts DC for Block 17 rooftop is actually a smart move. These panels are highly efficient, converting 20% of sunlight into electricity, and each panel produces 400 watts of power in ideal conditions. Hence, this high efficiency means fewer panels are needed to meet the power goals, maximizes the space roof, and also minimize the extra materials and labor. Despite their higher cost per watt, the efficiency and reduced number of panels make these monocrystalline panels cost-effective and also power efficient. Next, we had chose Shenzhen Sinexcel Electric's inverter for the project. So basically, the system's maximum AC power is 147,470 watts, and the chosen inverter matches this capacity. A higher capacity inverter is beneficial for several reasons. It allows for future expansion if more solar panels are added, avoiding the need of changing to a new inverter. It can also handle higher solar irradiance, preventing energy waste if the sunlight intensity is stronger than expected.
Hi, my name is Sarah Farina, and I will be explaining about the environmental effects and cost analysis on the extra specifications of the project. The specification of the solar panels to use high PMP monocrystalline panels will undeniably have a direct benefit to the environment, as it eliminates the use of non-renewable resources to generate electricity. The operation of these high PMP solar panels are fairly efficient, as it is capable of converting large amounts of solar energy into useful electricity compared to other conventional solar panels, such as polycrystalline or thin film solar panels. So this higher efficiency directly indicates a higher energy output for a given area, thus reducing the overall carbon footprint. However, while the selected solar panels that are made out of these monocrystalline serve numerous positive environmental effects, the extraction of these resources to produce these monocrystalline panels may have a detriment to the environment as well. Because in the production phase, the extraction of silicon involves the purification of this silicon, which is an energy-intensive activity involving high temperatures of up to 2000 degrees Celsius, which ultimately generates significant carbon emissions. Additional metallic materials, such as silver, copper, and aluminium, are also required to construct the panels, and the extractions of these metals also involve extensive mining processes that can lead to habitat destruction, water pollution, and energy use. The manufacturing of this monocrystalline silicon also consumes energy. So the manufacturing of these panels also involve corrosive chemicals such as sulfuric acid, hydrogen fluoride, hydrochloric acid, trichloroethylene, among other chemicals. So if these chemicals are not disposed of carefully, the environmental impact that is caused just by the manufacturing of these solar panels may also lead to catastrophic events. So at the end of the life for monocrystalline panels, the good news is the materials can be recycled to recover silicon, metal, and glass. However, the recycling can also be energy intensive and must be managed to prevent any additional environmental contamination. So it is recommended to use a proper disposal method for these panels to avoid environmental pollution. The use of high voltage inverters contains semiconductors, capacitors, and other electronic components that require metals and rare earth elements. So the extraction and processing of these materials also have high environmental impacts, which is similar to that mentioned of solar panels. The production of these inverters requires significant energy, contributing to greenhouse gas emissions, and they also typically have the use of rare metals. However, high voltage inverters have high efficiency, thus reducing energy losses to convert DC to AC power, which ultimately optimizes the use of the generated solar power. At the same time, the activity of using the high voltage inverters produces minimal heat. So the concern of releasing large heat energy into the environment is not a concern. However, this process must be managed to avoid environmental pollution once at the end of life. Improper disposal can also lead to electronic waste issues, such as soil and water contamination from heavy metals and other hazardous materials, such as cadmium and lead. So the cost of the installation and the use of these solar panels is significant for evaluating the financial viability and return on investment for the project, and enables the determination of the initial capital investment, any necessary maintenance costs, and potential savings on the energy bills. A cost analysis is also conducted to determine the break-even and payback period of the utilization of solar panels for the intention of cooling the academic building. So we have tabulated the parameters that is involved in the calculating of the costs and analysis, and we have found that 1 unit of 400-watt Hyundai Solar Mono All Black Bifacial Solar Panel cost is 870 ringgit. Considering we need 369 units, the total cost of these solar panels would be 321,030 ringgit. We have assumed that the installation fees and the delivery fees account for 10% each. So we have accounted that each of these fees is 32,103 ringgit. So the total capital investment would be 385,236 ringgit. The solar panels are warranted for 25 years with an annual degradation of 2% of the initial year and 0.54% linear degradation after the second year. So we have decided to utilize the solar panels until it reaches an performance of 70%. And the total lifespan before it reaches 70% would be 50 years. The electricity tariff for commercial buildings for Sri Iskandar, according to Tenaga Nasional Berhad, would be 36.5 cents per kilowatt hour. So considering the annual energy utilization, the annual bill saved would be 188,392 ringgit 93 cents. So once we have found the cumulative flow of savings, we have determined that the payback period is after the second year of use. So it is a fairly short payback period, considering the large savings from the solar panels that are contributing to the reduction of the electricity bills. We have also found that the rate of return is about 2,089.6%, compared to the initial capital investment, which would be 349,922 ringgit 80 cents. This is in consideration after 50 years of using the solar panels. So the annualized rate of return is 5.09%, and the rate of return is 5.09% per year for over a span of 50 years, thus making it a fairly decent rate of savings every year with the installation and the use of solar panels. So when we evaluate and compare the design of our solar panels compared to existing models, we can see that the monocrystalline solar panels have one of the highest advantages compared to polycrystalline, thin film, and the conventional power generators. In terms of efficiency, which is about 15 to 22%, while the conventional power generator does have a significantly high efficiency, it also has a very low space efficiency. And not only that, the operational and fuel cost is extremely high, and the lifespan also typically varies. So while matching monocrystalline to conventional power generators, it is comparatively similar. So we get the same quality, we get the same efficiency and optimization, but we have the plus point is that we have the advantage of reducing greenhouse gas emissions and toxic chemicals into the environment. So in addition to that, the additional features that make the monocrystalline solar panels much more attractive than polycrystalline and thin film is the fact that it has a better performance at higher temperatures. So when electricity generation produces or emits high heat, the monocrystalline solar panels is able to withstand these high temperatures, making it a less requirement for maintenance costs. The manufacturing is indeed more complex, but it also does not require that much environmental and resourceful impact as compared to the conventional power generators, because conventional power generators naturally use natural gas and fuel, and that requires a large amount of mining and extraction and drilling into the earth. Okay, so the operation is also silent, which is a plus point, especially when it is an academic building. So it doesn't emit noise pollution, especially when academic buildings are meant to be more of a quiet environment. And that makes the monocrystalline solar panels much better than the other solar panels. Thank you.
Now, let's go through the environmental impacts and economic analysis. I will be discussing the environmental impacts of implementing a solar PV-based cooling system for an academic building at University Technology Petronas. Firstly, this system significantly reduces the greenhouse gas emissions by harnessing solar energy instead of fossil fuel, aligning with global climate goals. Moreover, it decreases air pollution since traditional systems rely on electricity from charcoal or natural gas. Solar energy is not only abundant but also renewable, supporting the sustainable use of resources. Additionally, installing solar PV panels help reduce the urban heat island effect by providing shading and lowering cooling demand. Lastly, solar PV system has a long lifespan, typically 25 to 30 years, and require minimal maintenance, resulting in less waste compared to conventional systems. These benefits underscore the importance of adopting solar PV-based cooling systems, particularly in academic settings like UTP. Now, let's dive into the economic analysis of this project. Implementing a solar PV-based cooling system requires an initial investment in solar PV panels, inverters, and installation. Despite the high upfront costs, the long-term operational savings make these projects economically attractive. One of the most significant benefits is the reductions in electricity bills, as generating energy on-site minimizes dependency on grid electricity. Maintenance costs are also lower due to the minimal upkeep required for solar PV systems. So we can calculate the returns on investments by comparing cost saving to the initial expense. With the decreasing cost of the solar technology and possible government incentive, the payback period is becoming shorter. Incentives like tax credit, grants, and feed-in traffic can offset in the initial cost, making the project more feasible. Additionally, generating its own power shields the building from energy price fluctuations, providing financial stability. The installations can also increase the property value by making it more energy efficient and attractive to future investors and occupants. In summary, a solar PV-based cooling system at UTP is a smart investment that offers long-term economic benefits and support environmental sustainability.
So, in conclusion, designing and implementing a solar PV system for the cooling system of an academic building in UTP requires a forward-thinking approach that encompasses an economic benefit and environmental responsibility. So, the design of this solar PV system focuses on maximizing efficiency and ensuring the reliability of the solar PV system. So, monocrystalline solar panels are chosen due to their high efficiency and the lengthy lifespan. So these panels are integrated with high voltage inverters, which ensures an optimal performance and the energy conversion. So the cost analysis reveals that the initial investment in a solar PV system is quite substantial. The payback period is only after 2 years, and the rate of annualized investment, is 5.09%, making it a reliable and viable project. So solar PV systems require minimal maintenance, which also contributes to the cost savings over time. The undeniable environmental benefits of using solar PV systems is it replaces a large portion of the energy that is sourced from fossil fuels and natural gas, into natural new renewable solar energy, which ultimately decreases the building's carbon footprint. This this reduction is crucial, especially in combating climate change and promoting sustainability. It does not emit any additional air pollutants such as sulfur dioxide, nitrogen oxides, which is eventually harmful to the human health and the ecosystem. Last but not least, the integration of solar PV system is a strategic move that aligns with both economic and environmental objectives. So the initial investment, which is 300,000, is justified by long-term financial savings and reduces the environmental impact by a significant reduction. So this project truly exemplifies how universities can actually lead by example into adopting sustainable practices, and thus the investment into solar PV into this academics building is a very much encouraged movement. Thank you.